So we'll be considering in particular the Roberts flow driving. So we have a forcing term that is given by Roberts flow driving.
Special case.
Yeah.
And equatorial plane, and you have it.
I mean, I'm basically talking about the Tilden problem.
So important that for the part of the EMF we are interested in the alpha contributions as a will be 2 by 2 part of the alpha tensor.
I mean, I'm presenting this really because Matthias wanted to have this as a preparation for what he wanted to say. And this is actually part of an earlier paper which we wrote with Matthias and Karl-Heinz and Klaus Baumis and published in Update Letters last year. In those cases, we are considering steady state values of alpha and eta, and we confirmed the validity or self-consistency of the results by calculating the growth rate, which we can calculate because the coefficients are all linear, constant in space. So then this eta, then this is the total growth rate based on the dispersion relation. So,
So you,
yes?
formally it is non-linear problem.
Yeah. Yeah.
And what you say lambda, it means that no, lambda just you arrive to saturation, achieve saturation.
If you linearize about the nonlinear state, we
You find, of course, that yes.
if you linearize about the steady state, then we find that the
Gamma equals 0, of course.
gamma equals 0.
Lambda.
Now, I didn't know, I think I was probably not quite careful here because actually really now if we linearize about the steady state, we find that it's not, then we find that our solution is marginal, has a marginal growth rate, but it's not the most unstable mode yes, the most unstable mode is a marginal mode to the full nonlinear problem, with the MHD included, with the hydrodynamics included. However, if we only consider the induction equation for a given flow, we can ask again the question, what is the most unstable mode? We linearize about a state which was a solution to the previous problem, which was in saturation. So in other words, you're asking the question, is the magnetic field which has the name B as opposed to B tilde? B tilde is not the magnetic field of the previous problem. The magnetic field of the previous problem is B. The solution to that was a Beltrami field of this form. We can ask ourselves, is this Beltrami, if we have a hydro MHD state and we look for the stability around this state, what is the most unstable mode? And it turns out that it's not this one anymore. It's another one. And this mode has the name B tilde.
But B tilde is some artificial linear mode.
Yes, it's an artificial equation because all of a sudden we are decoupling. We are having a new equation. So altogether we could say we have the equation for the velocity field, du by dt. We have the magnetic field, dB by dt. And this is a nonlinear problem with J cross B here and everything, and U cross B. However, now we have a completely decoupling, not completely, it's a one-way coupled equation, because we have the same velocity field here, but now this magnetic field does not back react on this velocity field. And this problem in the context of both convective turbulence and for a shell model was addressed by Fausto Cataneo and Steve Tobias. Yes. And they found that indeed this solution to the for a nonlinear problem is not the most unstable mode for B tilde. Now, we addressed the same question after Fausto presented this finding in a talk in Santa Barbara. You were there? Were you there?
Where? In Santa
Santa
Barbara?
Barbara in July.
Yes.
I don't know.
I don't remember who made this. You?
No, as I said, it was a talk by Fausto Cataneo. And we
I'm
started
not sure.
looking at
I
that.
think unfortunately, we didn't meet with him. because we
Good.
didn't-
So,
it was-
so for the ABC fluid forcing,
Mhm.
this is the solution. The function B grows exponentially with what is the most unstable mode for a kinematic problem, where the flow is completely unaffected by the magnetic field. Then this magnetic field saturates and is constant. Not surprising. Now you will use the same magnetic field, velocity field.
But just a question of
Yes, yes. And you find it also grows initially because, of course, the velocity field is completely uniform. I mean, unaffected by the magnetic field, really. And then after this actual magnetic field has saturated, the B tilde field shows a continued increase.
it's the same growth rate as the linear part of real field.
It does not have to be. In this particular case, it is. And in fact, it can be in related cases even slightly faster.
Slightly faster.
Yeah. And I explain you why. It's well understood. We can, because we are dealing with a helical magnetic velocity field, or yes, because we are dealing with a helical velocity field, it makes sense to address the same question in terms of mean field theory, for which we have just previously calculated the alpha effect. So we actually know how this velocity field affects the mean behavior of any such equation. And this is using essentially for alpha as this type of tensor, and ignore for the time being the eta tensor, because it doesn't really change the story.
But V in this expression is just real field, not.
This is the real V.
Yeah.
Yes.
This.
Okay, so now let me ask what would be the magnetic field that is the least quenched by this expression. I didn't really say one thing. Let me see here whether it's on the previous page. Maybe even on the next page. In some sense, it's on the next page here, which are the results for this eta tensor. So what we see here is, but this is not. These are not numbers for the Roberts flows. These are numbers for travelers. We see that alpha 2 has the opposite sign to alpha itself. So alpha is positive, and alpha 2 is negative. So the quenching is achieved by having two different signs of these two different components. So quenching is being achieved by this and this becoming comparable to each other.
It's according to prediction of series, I remember. It's a different sign. Should be.
Yeah, I mean that's not very unsurprising. So how about choosing a magnetic field B tilde, which is actually
Orthogonalized.
which is orthogonal to this one? And of course you can find this. You just insert. You can just calculate the BI/BJ matrix from this field. This looks like this: has cosine squared, sine squared, and this here. And then you multiply with this vector, which is just the same as this one, but phase shifted by 90 degrees. You multiply this in here, and you get 0.
Right.
And so therefore, alpha ij bj just has a contribution from the first term, nothing from the second.
Understandable.
And in the cases of isotropic homogeneous turbulence, we normally find that both alpha 1 and alpha 2 are themselves B dependent, and they are decreasing with B. However, for the Roberts flow, they can actually be slightly increasing with B. You still have a quenching because this one increases faster than this one with the opposite sign, but they both increase with B for the Roberts flow. And so that can explain the situation where this one becomes faster than the other. The 90 degrees phase shift we see directly from three-dimensional simulations. If we look at different Z levels here, we see the same pattern copied if we phase shift by 90 degrees. That's all borne out and was first predicted by Tilgner using his weakly nonlinear theory based on the Roberts flow, which is in a paper, which is in an early paper by Tilgner and Busse. That's Busse. We should have actually talked to him about this.
It's not so early, this paper, after the Karlsruhe experiment.
Yes, 2001. Right. Is that all I needed to say?
Yeah.
Yeah. And then Matthias wanted me to ask if you can
Actually, to present that, well, the following. So we have learned from this example that the anisotropic part plays a crucial role. And what I want to say is not much. Only you remember. You remember the first nonlinear contribution to alpha. There was one part depending on the use. As I write it in this abbreviated form. And you said it could do something in the algebraic convention. Maybe this is true. This is perhaps algebraic. So we don't focus on that point.
Yeah.
And then there was a second contribution, which was expressible by the current in block as you remember. And this is
The same form in some sense. It's important. Because it's the same, if you like.
so. And from
You write IL on the left.
where's the L? Oh, sorry.
Yeah, okay.
This here.
It's okay.
Yeah. So I haven't put this into the integral, but I could have done. So now the reasoning was we know that alpha IL2 has to be a tensor of the structure. So, and we get the interesting coefficient alpha, which is again scalar, this order 2, as simply the sum of these two contributions, as Axel already showed.
Yeah, for the same field.
Yeah.
For the same.
And the question is how to do that. And it works by multiplying it by these two factors. And then if I do so, I get immediately.
Oh, just so. It's all that, yes.
But now you could maybe argue, perhaps the anisotropy is weak, and we have the permission to treat this tensor as an approximately isotropic.
No, in sense of electromotive force, you mean?
Yeah. So then let us treat this term. Let us focus only on this part as it would be isotropic thing. That is, we would get then what we want to get, namely alpha 2, simply as 1/3 alpha II2. Because we argue it is approximately isotropic. Yeah. And then
I don't understand.
wait a moment, then focus on this part only, and if you do so, you really get the desired result, namely this is then B1 curl B1 and the time arguments are that. And that's it. And then you get just the desired result, namely current helicity. Simply by treating this part as an isotropic
Of
thing.
course.
Yeah. It's quite simple. Quite elementary.
But why you distinguish that alpha 2 in this?
This is contained here. We assume that this should be the same. Calculating it this way, at least approximately. Well, that's a question. Could this be true?
I think it's. I'm not sure that you're completely right. Maybe I will.
They are, just want to say.
No,
not
one
right.
of
I just want to say I'm not right because this is quite reasonable to argue. Okay, maybe this is a wrong anisotropy, and
It's not wrong.
Not wrong. Sorry,
It's not
a
wrong.
weak anisotropy. That's why let us proceed in this way.
Uh-huh.
coming to the desired result. But what Axel presented just shows that the anisotropy is a quite relevant thing. So it's basically wrong to deny anisotropy.
Let me
And
say.
it's the only way to get this result.
Can I ask whether this expression in green on the second term in green has a form of the IVJ for the alpha? I don't think it has.
Yeah, in fact, something like that. This is a component of the current, this is a component of B. Yeah. And if you consider, if you treat this isotropically, then you get just the current density. That's true.
Can you show that? I don't see
So
that.
that's easy. Then put here as a second index L.
Can you just write it? It doesn't.
Yeah.
Or is it
So we put here instead of Li to do this operation.
yeah, then this I understand, of course, yes.
That's
But
what
I meant that you get from here to there.
from where to
To
where?
anything like this.
I
No,
think
I don't-
I think
I
it's
don't-
not.
I don't
It's
get
not
it.
true.
No, I don't get it.
Because you
It's
get
not
from
true,
there
Sim.
to also to here.
Sorry.
This is one thing, and this is another information that I use.
Yes.
It's
Yeah, yeah, but
independent information.
I think.
yeah, I understand. But why shouldn't this be related to a
Not
one of these
obvious.
two?
Yeah, of course it
It's
is.
not obvious, no.
I think just opposite. That this anisotropic contribution more associated with this term. Because what we demonstrate, it is possible to demonstrate
Yeah,
very
that's probably
easily,
true, yeah.
easily that magnetic contribution, Bj, nabla, Bi, epsilon, etc., proportional to integral k, say, IL.
Take away the pen, it doesn't, I can't read it.
Okay. KIL, AB, magnetic helicity, and D3K, and if you like, I, K, capital R capital, D3K. It means that the main contribution, in some sense, is isotropic, not anisotropic. And all tensorial behavior associated just with this term.
A times capital B,
A small b, A, B,
small b.
small b. So, no, in my
Yeah.
mini talk, maybe I will mention this again. So I'm not sure. My feeling that the main contribution to anisotropy to algebraic effect, not to from say dynamic effect. Okay.
Yeah.
But you don't have to say inform at least when we know your idea that all alpha effects may be constructed from induction equation, and you don't inform. I will inform from your permission about this point of view, and I explain why it's not a contradiction.
Yeah.
Should I start?
Yeah.
I tried to fix it. Should check whether
Why does it not work?
it takes some time to warm up. You can check whether he's interested in.
What?
Your father is not interested in this, or
In what?
what you're saying?
Doesn't matter.
Whether he's interested in what you're saying.
I think that what I would like to formulate that algebraic convention. Carl Heinz, you would like to say something about it? Maybe after my small presentation. Okay, let me start. So, single list.
Yeah.
In some sense, my presentation was a little bit, my pupil presentation, what I study about this subject. I would like to concentrate on the old question, how it's possible, from another hand, all information about electromotive force formally sit in equation of induction equation, and nevertheless we involve in our game of magnetic contribution, magnetic helicity. By the way, I would like to express why I so believe that this contribution really influence of anisotropic part, because magnetic part of alpha effect, if we just put this tensor of vector potential and magnetic field, we will find that the main contribution, this yellow term, is proportional to trace of this tensor, which means A dot B. And all tensorial structure just Km, Kn. It means that, of course, we can produce some anisotropy if this spectral density will be enough anisotropy. But nevertheless, general feeling that is more or less isotropic as a result of this representation.
So you have a second term, of course.
But second term, if you calculate a little bit, you will see that it will be second order in K capital, because
But,
you should very specific situation. Gradient, you need a simple gradient of large scale, large scale gradient of this kappa. So in general, our idea that the main contribution is from local. In this sense, it's very, how to say, convenient characteristic in order to calculate magnetic part of alpha effect. But let me start from the very beginning. I would like to demonstrate how magnetic contribution penetrate to theory.
but you just say that you could get an anisotropy maybe mostly through the U.
Yes.
And that of course looks very similar.
Yes. It's my idea.
But then you still have Ki, Km, Kn.
No.
No?
Just for isotropic case, Axel. But when isotropic, it will be this this complicated construction. It's a specific feature of magnetic part of alpha effect. This is because you cannot rewrite directly a dynamic contribution as some transformation of kinetic helicity.
So are you saying the magnetic part is more isotropic than the kinetic
Yes.
part? Yeah.
Yes, in this sense. Okay, let me start from the very beginning. This is, it's all people know, induction equation, Navier-Stokes equation, and we can split this.
This is more use of the fluctuations.
Excuse me? U in fluctuation, U will be fluctuating. But we can take into account mean velocity, but it's just some technical difference, nothing else. We can rewrite viscous storm because we study, for simplicity again, incompressible case as twice Coulomb. And we've got random force. Steering force is not convection, it's the most simple case, and one, how to say, what we should take into account, but it's maybe not so important for simplicity again, that B cross F average equals 0.
That's
It's
correct for delta correlated forcing.
Yes.
And
It
for
is,
steady forcing, it's not correct, of course.
what is it again?
For steady forcing, it's not correct.
For steady force, okay. But I think it's not so important even if you like. We will
Then
see
it is
then.
important.
Yeah, okay.
Then it actually does become important.
In situation with very large Reynolds numbers, it will be important. For small Reynolds number, it's less important.
No, especially for small, it's already important.
For small by dynamic you mean?
Yeah, and that explains why you get in one case a K to the minus
Okay, I
2,
agree.
K to the
K
to the minus B to the minus 2 forcing.
But nevertheless, we will see when it's important, when it doesn't important, if you like. Okay, so next step, trivial, we should split magnetic field two parts. I would like to concentrate. And what we find, equation for fluctuation. Means, of course, from equation for magnetic field, equation for velocity. Important thing what we need, of course, this is electromotive force, U cross B. Next step, let us discuss briefly what does it mean second order closure approximation. In this approximation, we drop nonlinear term 1, nonlinear term 2. This is, we can drop 2. And we've got very simple equation, with, which obviously can be written solution in this form, some green function. And after that, we immediately calculate this E tilde, and averaging gives us electromotive force, no sign of magnetic contribution. It's why Matthias believes that all these games with magnetic alpha effect just some kind of misleading. Am I right? Roughly speaking. Let me demonstrate why this is not in all situations, at least it's correct. Let's start from another. We can do alternative procedure to find exact equation for this quantity. In order to do so, let's multiply U cross first equation, B cross for left hand side second equation, and find difference between these two. And what we find? We find a lot of terms. We find first of all this kind of terms, which of course remember as hydrodynamic contribution. We find of course magnetic contribution. But let us pay attention what terms we dropped in previous consideration. We dropped this term, and we dropped this, and these two. What we do in this consideration? We don't drop these terms, because we combine terms from first equation and second in this manner. And it means that two terms cancel each other. As a result, we find that nonlinear terms, at least partially, accumulate in flux. So it means that if we do both approximations and we will be thinking about dropping of nonlinear terms, we will drop different terms. So Soka approximation, if you like our approximation, is not the same. Okay. Now after simple, you see it's a really trivial calculation what I do with it. Maybe, and unfortunately Igor don't demonstrate it 4 years ago in Cambridge because it was some turbulent discussion.
Yeah, but maybe at this point,
Karl-Heinz,
don't you have
some
a
comments
response
around
or
this?
something?
Have you got any comments? I think it's just formal, it's exact transformation, but it's just straightforward calculation. Until now we haven't any approximation. Next. Now we can rewrite our nice equation. It is fluctuation of electromotive force, or no, both mean and fluctuative part. And these two contributions. And what we find, nonlinear terms in our new equation, it's contribution of pressure. And second, something similar to alpha effect, but on fluctuative, which how to say, influence just on fluctuative field. Because alpha, the same alpha, there is two contributions, dynamic and magnetic one, and multiplied by fluctuative field. So it totally another nonlinearity than in Soka. And of course we have got flux, but flux we can drop as a result of homogeneous of turbulence, or weak in homogeneous. Okay. Now, after averaging, we can drop this term naturally because curl E it is average term. And this, according to our preposition, our idea that we know correlation. But if we can take into account it, it's not so important. And after this nice, how to say, averaging, we will find this very nice equation. Two sources of alpha effect. Most nonlinear, many of nonlinear terms accumulate in flux, and just this unusual a little bit nonlinearity.
It's linear, right?
Huh?
The last
Non-linearity. Why? What's
sorry,
linear?
yeah. Oh, the linear.
Non-linear.
Sure, yeah.
And non-linear.
Yeah.
If L linear and non-linear. Okay. So Soka again, what does it mean, Soka again? It means that we can drop several terms in this equation. We will drop, let us take this approximation, a real smallest Reynolds system. And Reynolds, whatever we like, no, at least less than 1. we can drop this term, we can drop this term, and we've got two terms. And we immediately restore, if we solve this equation, Soka result. But because it is possible to estimate on the basis of equation for magnetic helicity, second term much more smaller than the first. So we can drop it. So we restore Soka results. So Soka results restored in our equation when we've got very low magnetic Reynolds number. We know from the general theory, second situation where the Soka applied, it is small Struchl number. And of course, in this, what does it mean in this situation, small Struchl number? No, I think, maybe I will demonstrate next step, that in some sense difficult to control situation with enough small Struchl number. It means that we cannot drop f from this consideration in order to be sure that we've got small Struchl number. Until what we think the f not important, we cannot guarantee that the Struchl number will be small.
Well, if the Struchl number is small, we can drop it. We can
Opposite. In order to keep Struchl number small, we should keep strong f, and which somehow correlated with
the
b.
Struchl number small means stellar correlated in
Yes, it means that
for the velocity actually, not
for velocity also. But pay attention, it's possible because all these contributions proportional to velocity or to magnetic field. So it is very short correlated, it's possible to
yeah,
even.
but that has nothing to do then with the U cross, with the F cross B term.
F cross B term, what I dropped, it means that F in this sense not managed totally situation.
So we must keep it.
We must keep it.
Yeah, that's
Okay. So nevertheless I prefer don't keep it and to continue. Okay. So,
Nathan,
yes.
You dropped n there, no?
Yes, because this is according to magnetic Reynolds much smaller than unit, it means that all nonlinear terms are less than and this term is more important.
Yeah, but n here in the last line contains the last term, which is not quite clear to me.
No, this is just this difference. This contribution you not.
So it means it's just fluctuating.
Yes. So it is definitely it's small if Reynolds is small. So we really restore Soka result. No, practically no memory about magnetic contribution for small Reynolds number. It's true. Okay, now what will be in situation when let's some continuation, simple demonstration of what actually happened again. So it's obvious the solution of this equation is the same as the solution of result of Soka. Excuse me. Okay, now not Soka situation. It means that we've got Reynolds much more larger than 1, but dynamic Reynolds much less than 1. So-called high conductivity limit. What will be in this situation? In this situation, of course we can drop this term, we can drop this term, we can drop nonlinear. And of course, and again we can solve this equation for E. But what's new? New that we should take into account now equation for magnetic path of alpha effect. Because we should do something in this guy. We can write this equation, this usual E dot B, nothing new. Okay, in order to find E, we should somehow solve approximately. No, I made it in very, how to say, violent manner, excuse me. But more or less it's what's very plausible. And after that, we can, of course, replace alpha magnetic by alpha total, solve this equation in stationary case, and find algebraic catastrophic equation immediately. So, in a high conductivity limit, if we will be more careful, we should reproduce catastrophic equation immediately.
You have ignored gradients, yeah?
Yes.
Yes.
Yes, I will do it next step.
Mean current and stuff.
And this result, which we find, of course it's catastrophic equation, no doubt. because we remember RM much more than unit, so it was catastrophic. Okay.
How to explain it physically?
Huh?
How to explain it physically?
I explain it. Okay. Suppose we've got very large Reynolds number. As a result, magnetic field can increase according to induction equation enough strong. What can stop him? Just get none. Because nonlinear term is not important, and Reynolds is Reynolds small, so no dissipation, real dissipation. And this situation, magnetic field increase, but when magnetic field increase, it produces helicity, because we've got a dynamic contribution. And this helicity, due to resonability condition, have enough long evolution. So a magnetic helicity without flux begin to accumulate in our domain and stop generation.
Magnetic field, no, unit number say no 10 to the 12 something. The magnetic field strength is nothing.
Yeah, but you know answer. Alexander, you know answer. We don't take into account, how to say, surface of this celestial body, which of course will penetrate by flux of helicity and will, how to say, destroy catastrophic quenching. It's next step. Let me.
I'm confused because what Russell showed that we have catastrophic quenching for some particular configurations, like 2-dimensional that was originally
Catastrophic.
Einstein, yeah. I
Eh,
mean, two-dimensional
What I said was that
diffusion and for uniform magnetic field with no currents.
No, it is quenching for
what
2D.
I said was absolutely equivalent to this. And now Newton is in a particular limit where the mean current density is vanishing.
Yes,
I had exactly the same formula.
precisely, of course. All we
And
will
of course,
say
in
for
many cases,
years.
it's true.
Let me continue.
If you had a sun which was completely uniform and filling the full universe,
So
the
why
degree is conserved.
I think it's important to understand physically what's happening. You say that
Again,
you accumulate magnetic helicity and then
is this magnetic helicity? Is it magnetic helicity produce very strong magnetic part of alpha effect, which works against initial alpha? Because sign of magnetic of small scale magnetic field helicity just opposite to actual alpha. If you haven't another contributions, I mean B curl B or divergence of flux, and this term have sign which just opposite
Which is sum of kinetic and magnetic
yes, yes, of course. But you have got, say, positive sign of this sum, and the contribution will be negative. So it somehow try to keep situation, similar to thermodynamic, if you like.
Well, suppose I just ignore the second term.
What's the term? This one?
Magnetic number is very large. I just put it zero.
Okay, it will be the stationary situation.
Sasha wants to explain, you want to apply it to astrophysics or what?
The astrophysics is stupid because we've got flux. It's just model example, which gives
I'm
our.
just trying to understand the physics of this.
Okay, no, okay. You would like to drop it. You would like to drop it. To drop it.
Yes, yeah.
If we drop it, it will be an stationary situation. Alpha will be increase. When alpha tilde sum arrives to zero.
I mean, the physical situation would really be one where you ask yourself, what is the mean magnetic field in a periodic box?
It's another story, of course.
No, but that's addressed by this problem.
Yeah, I agree, but that's another side of the story.
But that's the corresponding physics. And Sasha, in that case, you know the answer, no?
Well, I know, from simulation to show, you had periodic box, you had uniform magnetic field, when you had quenching, here it's nothing like this, here it has some general relations.
It's the same.
It's the same.
And if you
Where's the
impose a
periodic box
magnetic
here? Where's the periodic box here?
if you impose a magnetic field for a periodic box,
No periodic box, because it's a solution, it's a solution. It is a boundary condition periodic box, if you like.
But catastrophic quenching was only for periodic box, or
Not only, not only.
From axis.
Not only.
If it's not periodic, then you don't have catastrophic quenching.
If you,
but here's at the moment periodic.
no, it's equivalent to periodic because we
Yeah.
closed our box for flux of helicity. We dropped flux of helicity from our consideration. let me continue, Sasha, maybe it will be
But
more.
on the other hand,
And after come back
at
if you
this
need.
point, we must have lost already Matthias and Heinz, I guess.
What do you
I think
think
we lost
about it?
everybody now.
Huh?
I think we lost everybody now. We can continue, but you know, if you
No, 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 no.
We have to
If,
explain
let us continue, but it's nothing with my consideration.
But
It's
actually
just,
understand, you know, what you're saying, but you know,
It's
so I
just-
don't know.
No, I mean, it is completely equivalent with what I explained already.
I know, but you know, what from my understanding, of, I repeated several times, you know, understanding of your talk, we have first catastrophic quenching was Catania-Weinstein simulations of diffusion two-dimensional.
it's another
Pure
story.
two-dimensional effect. That was first
Because you know,
catastrophic
Sasha, let me explain. Why is it not the same? Why is it, formula is not the
interrupting
same.
me, you know.
But I understand what you're saying. Okay.
The second catastrophic quenching was alpha quenching, when we have a periodic box and uniform without currents, uniform magnetic field.
Mhm.
What's equivalent to this here? Which situation? Because you know, there's no. If you have no uniform field or non-periodic boundary conditions, no catastrophic quenching. That was learned from Axel.
Correct. And now look at
What
this.
what
We
here?
know-
What
we
we
know
learned
it's
here?
constant,
Periodic
right?
box.
Without this concept,
So it's a uniform field.
uniform field, so
Exactly the
means
same
that
thing.
no big will be torn.
Yeah. There's no
Uh,
big current.
Let me explain. Let me answer first
Do you agree then?
first question. First question. Let me answer on your first question. When I spoke about 2D turbulence, it's totally another situation. Why? Because 2D turbulence has another integral of motion. It is curl V in square. It is new integral of motion, which play a role in this dynamics of helicity. And the base of this conservation, they find the same result for catastrophic quenching of diffusivity as in 3D exists catastrophic quenching for us. It's not the same. It's similar, but not the same. So they never demonstrate that magnetic diffusion in 3D catastrophically quenched. Just for alpha effect. They demonstrate.
We demonstrated the opposite, of course.
Yes, of course. Axel demonstrated his calculation that never in 3D no catastrophic quenching of turbulent
From
diffusion.
some degenerate cases, you know, like you know, 2D or
No, 2D
periodic
is,
boxes, no currents, you know, that's only two stations we learned, you know. That.
Yeah, that's
2D
right.
is, it is not simple degenerate situation. It's another physics and sense of the 2D has another integral of motion. And-
I understand the physics here.
Yeah, no, physics here is something trivial, and maybe I don't understand all. This is correct equation. Agrees, it's true. It's equation from just two-line calculation. According to this equation, we've got electromotive force with both two contributions, magnetic and dynamic one. For magnetic contribution,
And B is not necessarily uniform, right?
necessary uniform. Because if it's not uniform, we've got additional term in this equation. Minus eta B curl B. It is necessary uniform.
And then there is no catastrophic quenching.
No catastrophic
Why
quenching.
we are talking about catastrophic quenching then?
I speak about catastrophic quenching because originally catastrophic quenching in works in our seminal paper in 1982 and in Gruzinov paper, and all guys arrived when we study just homogeneous or almost homogeneous magnetic field. But because Reynolds is huge, especially in astrophysical situation, enough very weak current in order to change all situation drastically.
So now let me ask what you want to explain now. Because
Now I would like to know
know.
what does it mean tau approximation next step,
Uh-huh.
if you like. Of course, I can stop at this moment because I think in general, I have solved my, how to say, I achieved my aim, explained how to understand the result of SOCA for, in our understanding of
Yes.
magnetic contribution. I
Yes.
think I believe that, well, I understand, I hope so. But next step, what actually formal
It
happened
was
with,
confusing because you said, of course, any theory should reproduce catastrophic quenching, and that's what
say again.
you said that, you know, that you reproduce catastrophic quenching, that is good for a theory, no, but
Yes, but I know how to destroy catastrophic quenching. In order to do so, enough not to take into account, how to say, periodic boundary condition symbol, not enough. We should open this domain, numerical simulation, for magnetic flux, for flux of magnetic helicity, and after that we will restore normal situation. No, roughly speaking, what happened?
But I mean, there is of course the problem that already with this case of a uniform field, I think there is a conceptual difficulty because I think Matthias and Karl-Heinz, they don't agree with
What?
this. At this
Okay,
point.
let's listen what says.
You can neither say that they agree nor that they not agree.
But
Simply have to look in the answer.
you okay? With great pleasure. I will send you. I will give you simple by disconti. It is serial not two, but serial calculation. It's enough simple. You can. But again, physically.
Maybe that's important now. I mean, I thought I know the rest of the story, but maybe I don't. I mean, maybe you should tell me what the rest of the story is, and then we go back to these three lines. But
Okay.
Because
Okay.
we want to
No.
clarify
Okay.
the issue of
Okay.
cost.
Okay. I put this one. I find this nice equation, which solution is obvious. And now not so again, and now more interesting in physics case. Limit both Reynolds is large. In this situation, we can drop both dissipative terms and flux, and we've got again simple equation with non-linear term. Next step, we introduce so-called tau approximation. General idea of this approximation is if we switch off magnetic field, somehow our situation should be relaxed and electromotive force should tend to zero for enough long time. If we do so, we can, and assume so, we can of course approximate this process by simple tau approximation. We can do it more sophisticated way, to do it in case space, but it's some technical problems and nothing else. Okay, now we've got two equations, one of helicity, one of electromotive force. And again, we will solve this. We will solve, but let me now I will demonstrate what happens if we involve in game additional term with current. It's special for you, Sasha. We involve in our play this current. If we do it, immediately we've got new additional term. And we will not drop this guy. And if this situation we can simple drop these terms easily. Because system very quickly forgot about both kinetic helicity and what is.
Then we have same equation as we derive from conservation of magnetic helicity.
You know, you will be right if flux will be equal with sign minus for large scale helicity and small scale helicity, but it's not the same. It is one of the very, how to say, not so trivial place, which normally in China all people thought that it's true. A dot B capital equal A average A small B small. It's wrong because flux is not the same. So it is not so trivial. We should be more careful with stuff.
So what's the definition of phi?
Of phi? No, I honestly speaking, I don't remember by heart, but maybe I've got. Okay, well, it's several. First of all, it's U capital multiplied by helicity. After that, something.
It's alpha.
Alpha.
Huh?
You.
No, alpha. My alpha. And it's first. So, second, U say cross B I something. Right. Many, seven, not seven, four terms. I will demonstrate you if you like.
Okay.
I've got.
Okay.
So, and of course we don't know precisely what the value, but what I would like to say, we can open this and find this is term just B dot A. Use small alpha m. Next step, it's average.
No, not like this.
Like this, one is a term. No, how you find
No,
it?
I mean, this has a direction thing, either in the, I mean, the above equation is probably wrong.
Huh? This equation is not the
Goes
problem.
to the left. The triple thing is not right.
No, excuse me, please. U cross BA, it exists, right? U cross, so it means you've got two terms. B might be silent.
But obviously you don't have
B-
a contribution along the direction of U here, if that's a... If
Okay, opposite. Maybe.
Yeah.
Yes, right. Something,
Yes.
something in this spirit. A. Yes, I think so. B, no.
Yeah, but anyway.
Okay, anyway, we've got this term.
Yes, sure.
And then we average this term. We can do it in this manner. D E alpha m dx say multiply some scale. And scale multiplied u is diffusion coefficient. It's obvious in homogeneous situation no effect. And if we now rewrite in some, of course it is hand wave arguments, I agree. But at least in how to say, some way to understand what actually happened.
Yeah, yeah.
So I think the main term is this one,
Ah.
which is associated with diffusion.
I think, of course, the main term is the what I call Vishniac and Choplex.
I don't think so. In what sense? Maybe for equation
We
is yes.
we have demonstrated this with a number of different simulations which are homogeneous and they have shear. And catastrophic quenching is alleviated.
Yes.
Conversely, we have situations with no shear where we do have inhomogeneity through the effect of open boundaries. And that catastrophic quenching is not alleviated.
Maybe turbulence is not enough developed.
So at the moment the evidence speaks for Vishniac and Choplex.
Okay, I wouldn't like to discuss with you because, but I don't know. But what I know for sure, I don't know enough examples when this contribution, diffusion-like contribution, doesn't exist at all. If it's true what you say, it will be first example in turbulence.
Yeah, yeah. No, I know. I mean,
Okay.
let's talk about the evidence, and I know it should be there, but I also have seen that I haven't seen it yet.
Yes, actually, let us discuss, but let me maybe come back. So now we can.
It's confusing because we don't have expression for phi.
Yeah, I can write for you expression for
Well, that's
phi.
what you just wrote, and then there's a Vishniac and Choplex, which I can also write down. You want me to write it down?
The reason that you know, we basically, okay.
Then,
You remember?
yes, of course. So that's your phi, essentially. So phi is, of course, a vector, and that's whatever that is. And then there's another contribution, and that
I mean, in terms of large scale.
B gradient phi.
let me call this.
In terms of large scale.
Yes, yes,
Okay.
this comes now. So now we
It's
have
possible.
CVC, that's a Vishniac and Choplex. And show the coefficient times S is the matrix times B, the mean field, crossed into the mean field. And this is a number which I believe is of order unity.
S is shear.
And S is shear, yes. Sij, this is this one, is U bar, and this is I comma j plus uj comma I times a half.
I agree with you. It is small. At large scale. You
Yes,
mean at large.
yes.
Okay. Yes, maybe this term exists. Nothing against. Question is why you have a small scale contribution in this way.
So it just, it's starting from minus, right? So
Huh? Minus.
So this is phi, right? No, not this part.
Everything.
Everything.
Everything
is
Just
phi.
a small
Three
scale.
terms. This, and
And we want
this.
to see.
I would like to check
Large
sign
scale.
of this term. This is B cross A cross U something.
So it's a part of phi, right?
No, it's all phi. Additional term. No, let's say another. Friends, I can, if you, several minutes would take my papers, give you exact expression. After that, Axel find some approximation of average flux, which, according to Chu and Vishniac, right? It is Chu and Vishniac flux, which he formulate for operation disk, if I remember correct. We formulate another flux, which actually gradient alpha kinetic multiplied by b squared. We find in our calculation this kind of flux. I don't remember, maybe with minus, it should be checked. No, it is again not so, how to say, good calculation, we know it. But plausible another contribution, say b squared multiplied gradient rho. gradient rho, maybe something in this spirit. Maybe B omega, for example. And so on and so on. So, our feeling in general, that, and of course, the additional contribution minus some coefficient, some kappa coefficient of diffusion, and alpha magnetic. And I'm pretty sure that in all situations this term exists. Another question, what's the value of this coefficient? Maybe it's small, maybe not. But hard to believe that, that in this situation, which in some sense not so different from normal integral of motion, that we have this term, which just described turbulent diffusion.
And if it's it alleviates catastrophic quenching through the equator.
Say again.
If it's there, it does alleviate catastrophic quenching through fluxes through the equator, but that works only for a dipolar mode, by the way. It's interesting. It works only for dipolar modes. It does not work
Because for
quadrupole modes.
quadrupole mode equals 0. That's great.
What?
Because for quadrupole mode, I think it is gradient equals 0. Okay, ladies and gentlemen, in some sense I came again to this nice presentation, which again demonstrated, in my view, isotropic nature of magnetic contribution. And so, thanks a lot for your attention.
So that means thank you. So let's go back to the main problem then.
Yeah. Could you print out the first page of the
Of course, print.
No.
show?
Ah,
First
okay.
No,
No, not this. This?
not before.
Before it, okay, this.
Okay.
No, no. Yeah.
Okay. Excuse me, I need to go with you. Maybe you mean this one.
Well, it's too late.
Okay. No, it is, what actually happened, I accumulate this term, and this term, and this one. So, after that I have got this, and this.
Yeah.
And they compensate each other in sense that they produce flux. It is not so, how to say, strange. Because if you take u dot b and v dot in this position, and soon it will be integral of motion. And written that an integral of motion is the same compensation. Just in this situation a little bit more sophisticated than zero. So my claim that the electromotive force close to integral of motion, not precisely integral of motion, but close. As a result, in this two approximation, we in general drop different terms. So part of this term which we dropped, I mean this one, we recalculate somehow by second equation. It's my mathematical.
So why do Matthias and
No, because Matthias drove this term. And I
yeah.
try to write something instead of this drop term. It is nothing else.
I know that in this derivation, if you take the two equations as cross term plus u and this b, that then this expression u nabla u and b nabla u occurs, and that you can interpret them as
Flux.
kinematic, no, as kinetic alpha effect and
You mean
No, no.
this one?
yeah.
No, I can interpret, of course I agree with you, I can interpret, but problem is, why this term doesn't appear in you? In some sense you drop this term. What we can do? We can find this term multiplied by u cross from second equation and just put it. How we can do it? We take this term multiplied by this b, use this identity, and replaced these two. And in this situation we involve all equation of motion. So, of course, for large magnetic diffusivity, which is term is diminished, all of these contributions are not so important, but if not, maybe important.
I can rate, and may I ask why you developed the car B0? So, I mean, why you developed
What, F?
I mean,
What you-
large scale electric current.
Why I drop B cross F? Why I drop B cross F, you mean?
Car B0. B0 is uniform field.
Yes, yes. In practically in all my consideration, B is, for simplicity just, B0 is a homogeneous field. It means that we haven't large scale current. Of course I can do it. I should add some large scale terms which proportional to current, but easily.
The objective.
Just say me, I will do it. But
Yeah.
but it's a technical question in order to demonstrate just magnetic contribution to alpha field. Magnetic contribution to turbulent diffusivity, magnetic turbulent diffusivity, first of all equals zero in isotropic situation in linear approximation. And second, not, how to say, subject of catastrophic quenching, at least in 3D situations. So I don't think it is so important, at least in context of my presentation.
So the concept, the issue is to identify why there is a conceptual disagreement of whether or not the little j dot b term should be included as a result of feedback or should not be included. So we have to boil it down to strip away every possible ballast and go to the minimum.
Minimal
And
system
of
is
course, you can
described.
always make more stuff, including currents. You can, but you want to drop every ballast now. You're going to reduce it to the minimum. So I think in your situation, you have to be clearly in a case where
Excuse me, I will bring my charger.
you are in the limit where the magnetic transfer is larger than 1 already, and I think that's critical. And then, of course, SOCA is already out of the game, at least unless we have the SOCA, and unless we have a Storhal argument.
What worries me is in Nathan's derivation, you have always U and B, or also U and the other U at the same time. In
Yes,
In-
sorry,
in
I just want
SOCA,
to write down this
you
one.
have the correlation of such quantities at different times. And it seems natural that you consider
That's your
that.
limit, yeah?
Right.
Okay, no.
Sorry. Wait until he listens. Maybe we don't need your computer. Do we need your computer?
No, better. Because you know, it is calculation.
Maybe even worse, because then we don't have this whiteboard.
Okay, we can go up.
So now, we say again.
Yeah, what I said, in SOCA, we get for alpha, beta, and so expressions, where is a correlation between U at one time and U at another time. And I think it is
It will be
easy to understand.
Uh-huh.
Oh, I wonder, here in your derivations, you have always U at the same time, or B at the same time. Of course, you derive an equation for dE over dt. So
It's the
you
same
haven't
time.
played out the time, but this worries me, that you have always expressions where you take the 2U or the 2B at the same time.
Karl-Heinz, I can find equation for correlator U cross B,
Yeah.
U in one time, B in another time. Solve at least.
No, I think I'm not interested in U cross B with different times of U and B.
Karl-Heinz,
The
let me-
quantity
let-
which
let
I'm
me finish.
interested in is, sorry, is the average over
And-
U and B at the same time.
Yes, but I can solve this equation, or find this equation for different t. After that, imply hypothesis about homogeneity of our correlated. Solve this equation now in respect to with diffusion losses, and put in the end t equal t1 equal t2. I think you know, Karl.
Maybe can I ask the following? Karl-Heinz is thinking about it, an equation for E.
Yeah.
But this is, of course, never what Nathan and I would agree with that, want, because we want an equation for dE by dt.
Yes.
Do you think in that
Yeah.
case too you will have a time correlator? Yeah? Maybe you can tell us, show us.
Okay. Karl-Heinz, what you okay?
I don't know whether it's the solution of the problem, but in soccer, your E is
But in soccer, we now want a dE by dt specifically.
Yes.
yeah, but
It's
what I
true.
know is that it's some integral. I write it very.
This, you mean these two, this will not at the same time?
Sure.
Okay.
Say minus
That's up to
Tau
in
and
this case,
Yes,
yes.
that integral over top.
Yes.
You derive t over dt, and in this expression occur only u, t, u at the same time t, and
Yes.
also e, t,
Yes.
b at the same time.
Yes.
This worries me a bit. What is the reason for that? Even if you carry out this integration, it remains that you consider correlations, if you always correlations, at the same time.
Karl-Heinz, let us concentrate on what subject. We discuss now situation which with small magnetic Reynolds number or arbitrarily. It's not in our theory. It's
Even
not the same.
arbitrary, I think. At this point, even arbitrary.
No.
I think it is what can it is high not high okay, small Struppel number limit. What you wrote, right?
I wouldn't like to discuss about such limits.
Because
Take
in-
the original equations without an approximation for small or large parameters.
Can you explain perhaps how you envisage getting
Without super.
time correlators in this? I mean, here it's clear how you get it, because you get it from the Green's function.
No, it's not from the function. It's just
That is a
integral
technical
error.
aspect, but
It's of course from the Green's function, because you have a time integration.
sorry,
Yeah.
say it again.
You have a time integration and a space integration. That's
Yeah.
why
You mean
Yeah.
but
that
here we don't have a Green's function.
Yeah, where? In our consideration.
In this.
We have good Green function. Why not?
Well,
We have good just a moment. I will demonstrate. This one. If we try to find this correlation, I will rewrite my
yeah,
question.
okay. This is a molecular diffusion, yeah?
Yes, and
Yeah,
I,
okay.
yes, it's soccer. Yeah,
And for the molecular diffusion, I agree.
Yes, for molecular diffusion we have got green function. If you like tau approximation, I can rewrite in form of green function in case space.
Yeah.
So it's
That's
something
what-
that's a technical problem.
No, but-
I know this. Again, it may be something. In my view, maybe I'm not right. Of course, we've got a little bit another way, but we've got, of course, green function in this equation.
I mean, that really comes about because you pick up contributions to E, of course, on the right-hand side through the Green function. Yeah, that's obvious.
So
I mean, in
I
that case, but from all the other terms that are independent of the EMF, like all the first order terms here,
but
there's no reason that there should be a time correlator coming in.
Yes, that's my point. I see one way where this correlation in time occurs, and I don't see how it happens on the other way.
no, what we can do, we can rewrite this equation in K space and we restore this formula at least very similar to U. You know, we made it many times in Potsdam. So it's a, okay, small difference, nevertheless. exist, because it's a little bit not the same theory. But in general, we cover a result of SOC.
Sorry, you?
In general, for small Reynolds number, we cover restored result of SOC. Because if I will rewrite in K-space, I will restore this.
Yeah. That's of course also what can do, and
Well, what can I do? I average. I cannot not average if you like. I got the average, and after that again restore and solve exact equation, no, in this approximation. And after
So
that average.
So in explicit, I mean, correctly speaking, then this is not correct. It's still a correlator.
Yes, of course. If I will do.
Yes,
if
if
I
it
will
was
say-
In X or?
Both, yes, of course.
Karl-Heinz, pay attention. You find it after averages.
Sorry, I don't see it. You
Okay,
write
let me demonstrate.
It's only an X, yeah? Yeah, for the diffusion, yes, of course. For the diffusion operator, it's only an X.
Only
Okay, this is exact. What?
For the, if you only want to treat the diffusion operator, it's only an X, of course.
Yeah.
Let's do something else. Let us don't average in this moment. Just drop nonlinear to this term is small, nonlinear because it's not small in this one.
Yeah, so then,
So we've got this exact.
yes, so
Representation.
would you then agree that there is no true time?
Will be the I think will. If we now go to omega k omega space.
cannot change anything.
Why it's not change anything?
Because they are equivalent.
Yes.
Yeah.
Physical space.
Yes. It is equivalent. It's equivalent, friends. I agree. It's equivalent. But I think it is okay. Maybe, of course, we can discuss now several months what is this
No,
small
but
difference.
you agree then, yeah?
I agree. It is not. But for me, honestly speaking, it's not so serious.
Yeah, but okay, but that's fine. So because I also agree, and then there is such not such. And how can you then envisage? You were saying I was asking you what would happen if you were to develop a theory for this quantity.
Yeah.
It's a legitimate question. You do it in first order smoothing. I cannot see either how there should be a true time correlator.
Yeah. And that's my problem. I don't see how to reconcile this.
I now understand what is question. Maybe this not instantaneous correlator UU somehow associate with magnetic contribution. No.
Sorry?
This non-instantaneous UU, which
Yeah.
we've got
Yeah,
in
yeah.
integral, somehow associate with magnetic contribution. Another representation of magnetic, maybe it's another representation of magnetic contribution. Is U in some sense here. Because this is exact calculation, precisely as a soccer.
No. I see. And
It is amazing.
That's what that is a problem.
Problem in what sense?
Suppose-
We should understand what does it mean. It's not problem.
Nathan,
Generally, it's not, I think.
Yeah.
coming back to the magnetic alpha contribution. So I would not deny that there is such a contribution. The
Say again,
derivation I've shown demonstrate that there is a magnetic contribution to alpha due to quenching.
Yeah,
What I deny is that this contribution is isotropic. And you say now, if you do something better like SOCA, namely a sort of tau approximation, which
It's not tau approximation.
Or-
Until this equation, it's just exact equation.
with something better than SOCA, then you get, instead of the anisotropic contribution, an isotropic one. Is this- is this a-
No. It doesn't how to say associate is in this approximation directly. It is something which in parallel exists. Let me demonstrate if you like.
Now my only question is, do you really get an isotropic contribution, magnetic contribution to alpha due to quenching? Can you say yes or no?
I've got magnetic contribution to alpha.
Isotropic.
No, general. And after, when I try to recalculate this contribution via magnetic helicity, as in this line, I will see that it's associated with trace of tensor A, B, H. So it means that it's A dot H, so it is magnetic helicity. An all tensorial structure, in first approximation at least.
But this means isotropic.
No, because who said you that the kappa or helicity really isotropic scalar? It depends on K somehow.
Yeah, the dependence on K is not the point. My anisotropy comes from the dependence on the direction.
No,
and it's not there. No?
no, that's the point. Can you imagine that this kappa, this kappa function on B, K, and KB? Right? In this case, it will be isotropic
Okay.
after integration.
So there is perhaps no contradiction.
No, in general, no. But my point another, that in general we deal with isotropic part of magnetic helicity. Maximum isotropic part. Maximum isotropic.
And why not with the anisotropic?
No, because you've got tensorial structure in general. We can imagine this position something like, no, you know, because it's divergence, we haven't this terms. You're right. It is one of the, because with B divergence B equals 0, we haven't additional terms in this place. Divergence B equals 0, it means that, say, K, M, K, what it is? Km, Kn, Khn, for example. Yes? And Km, P, say. We haven't this, because divergence equals 0.
But then the whole side.
But this is capital. You can, it is possible to
Yeah.
demonstrate that all these
Yeah.
proportional to capital. Capital means large-scale derivatives.
Right, but if I assume a homogeneous situation, then all these
Strong
terms
in the
disappear.
material. Right. Homogeneous, yes, all
Yeah.
this
And
disappear.
then you say the first term disappears too.
Well, how it disappear?
You said just with like.
No. Suppose we've got another. We've got Km with A, kappa M, and Kn in this position.
Which we don't have.
We don't, we had, but because we've got
Yeah.
divergence free.
Okay. We need not to speak about it.
Uh-huh.
We need
Oh, but I explain why we haven't this.
But we should speak about this point, and there you really get something which is an isotropic.
Possible anisotropic, because we've got this. It's plausible, more than plausible. It's very. I think it's just in this. Of course,
Yeah.
no doubt.
Absolutely.
So in this sense, no contradiction.
There is no contradiction.
Yeah, right.
So we should expect that in general, if the evacuation of the mean field plays a role, we won't recover the isotropic sort of magnetic alpha J dot B average.
It will be for very weak magnetic field, because for very weak magnetic field, we can simply drop this guy. And it means that for very weak magnetic field, if it's isotropic, we immediately find that this integral equal delta M. So it will restore the isotropic field.
No doubt. Yeah.
So, you know, in some sense, I think we more or less covered all plausible situations. Okay,
Okay. Yeah. Okay.
Axel, what do you think? It is more or
I
less
think
interesting.
this needs to be
Checked again.
whether it's isotropic. I mean, it's obviously not a big issue, I would have thought, because if it's not isotropic, we would have to use an anisotropic quenching formula, which I would expect is not so different from the.
Yeah. The
Okay,
problem,
maybe
the
should-
problem is linked to the helicity balance equation. The helicity balance equation contains only the isotropic thing. And you get
Yes,
no
for
guess
definition.
If the thing is anisotropic.
But you know, we've got our paper
Okay,
of
so I'm
1999.
typing it in.
We analyzed
I have
I
it
need
across. It's just
this
that-
tensor. Behavior of this tensor. Maybe we should come back again.
Yeah, but with respect to helicity conservation equation, you have no freedom. You're obliged to use there the isotropic
No.
expression.
No, it is just question how deep we study transport of magnetic fields. If we will do it enough deep, if we continue our study, which we, for some historical reason we stopped in 1999, because the way it is isotropic equation, I think we can find something which will be useful.
I have impression that Soka is waiting for low magnetic resonance number. It's equivalent to.
Not only. If you can control Struckel by strong force in you, equation for velocity field. It will be good. I've got doubt just for high conductivity limit and not small Stropel number. The one case where we've got some, how to say, no, not contradiction, because I'm not sure that we can do from one hand high conductivity limit and small Stropel number may be in contradiction. No, I don't know. No. So what you need? You need to organize your field, your force, in order to avoid helical contributions, magnetic helical contributions. If you do it, you will restore, of course, Soccer results. So, but it's of course difficult. It is very specific magnetic field which is similar to the diamond Dayval of Maxwell. Which no catch each portion of liquid, somehow organized force. So I don't know.
Still, for practical purpose, we'd like to have, this expression for phi naught. And
Phi naught,
you wrote different expressions. You have some kind of diffusion flux. Axel has a much more
we've got
complicated
contradiction with Axel in this point, because I'm pretty sure, according to all our experience in turbulence, we should have this term.
The diffuser.
Yes.
It's mostly diffusion fluxes, and what was the physical mechanism for this?
I explain.
I mean,
Explain the mechanism. We've got this term, it is obvious, right? Light scale velocity.
So this is phi naught equal to this. Can you start writing from phi naught equal to?
This is obvious. This is what this term, right? Just in sign minutes.
And this is chi is the same as alpha, right?
No. No, for some alpha. Right? Alpha. Okay, second term it should be average U alpha M. No, because it is before averaging, they exist together.
Okay, so how express in terms of...
Next step, but in homogeneous turbulence it should be zero. Let us put alpha as d alpha, dxi, and I. And I some vector. Let's take some reference point. In the homogeneous situation, this contribution equals zero. In non-homogeneous, yes, it exists. So, and we put this. And then we immediately will find, of course, it is approximate. It's not how mathematically proved. It is some, but it's not just wave, hand wave argument. It's a little bit more deeper. U alpha m minus U alpha naught m. This is 0 and minus U L I d alpha dx d alpha dx. Okay, and I would say that is approximately equal alpha Li d alpha and dx. And this term, of course,
Gradient. So the gradient of
this gradient and this is some diffusion.
some diffusion coefficient.
Of course, I think honestly speaking, you've got G because you should divergence. It is G.
by the way, if you, I mean, I have the numbers actually in front of me here for the anisotropy, but how much would you regard we need for this to be called anisotropic? I mean, I think the anisotropy is less than a factor of 2.
You actually, what about what you speak about contribution to anisotropy of alpha K? B proportional to B.
Both of them.
So,
No,
Sasha,
for
I think that is, of course, it's not how to say improvement,
MHD
but at least demonstration of what we can.
So if you say solve from computer, this equation, so we take just the first term, if U is this capital U
It's related on circulation,
and differential rotation.
but of course, if you've got some eruptions in active regions.
No, we just solve the 2D dynamo problem, okay?
We speak about 2D dynamo.
Yes, yeah. So
Yeah, in some sense it's not so important because divergence of this term will be zero. What actually exists, of course, what will be, I think, it will be lambda u
not necessarily
multiplied
zero,
by
it's
alpha m.
alpha is a function of radius and
Yeah,
latitude.
I agree. You've got two terms, u nabla alpha m, and additional term with elastic approximation, lambda minus the entropy divided by rho. I try to explain how to
So
understand
you
it.
just transport,
Yes.
alpha transport.
Yeah, of course.
And then add a turbulent diffusion.
It will be, yeah, but exists nevertheless. Vishnu term, our term, and additional terms exist. Because, you know, it is a bit naive what it is not all stuff, we've got additional terms. And additional terms, no, for example, what's term additional? For example, we've got equation for phi. And this, we've got term phi dot b, for example. And to find this term is not so simple job.
Also, when you do this expansion alpha, the neglected dependence on time. This.
I neglected dependence on time.
But if you include dependence on time.
If I get no dependence on time, so what will be? Well, let's try.
We have the alpha, have gradient alpha, right? But also that's
Okay, let us
time,
do it.
right?
Let us do it time.
And
What we have got? We have got u tau, just nothing else. And obviously, average equals 0.
Average is 0.
Yes. And this is not, because it's a correlator displacement and velocity. It is, in some sense, displacement. And of course, it urgently gives it. So it's not the same. It is, how to say, we thought about it, of course, before. We never wrote, it's true. Because, of course, it's not it's not serious.
Can you write now the final equation
For flux?
Yes, yeah.
Okay, let me, it's my, okay.
And then we'll
Okay,
use it.
I will write, actually will say I write wrong. Let's see,
Irina did this equation, yeah.
Okay. First of all, what we should take into account that alpha is pseudoscalar, right? And so our full flux should be pseudoscalar. First term,
So what do you want, the flux, yeah?
Yeah,
pseudo-vector. Flux should be
That's a reduced
pseudo-vector.
2D dynamo model.
Yeah, but you just take, I just print you the paper.
Okay, no, okay, kappa. Gradient alpha, yeah. You know, Sasha, I would like to say, no, okay, I will write, and after that I've got some comments, practical, for the, okay, it exists,
That's what I mean.
It's a gradient, I mean gradient alpha.
yes, gradient, of course. Is,
Minus and
right?
Yes.
See,
don't discuss this,
what?
And then it's with a plus sign, by the way.
What this?
Uh-huh.
See, some coefficient. And by the way, what about unit?
By
Dimension.
the way, the flux, the U term is also a plus sign.
Huh?
The first term is also a plus sign, of course. The flux is in the direction of the midpoint flow.
Mm-hmm. Right, of course. I agree. I agree with you.
So alpha m is only a placeholder for j dot p.
No.
Fluctuations.
No, this is, no. This is old story. You have got some, because we've got this expression, the two helicities associated via some local local expression. Because if you integrate it, you got 1 divided by typical scale.
But I mean, in the derivation of the elasticity balance, where this flux term occurs, then
Yeah.
I would not expect
It is magnetic.
something very complicated. It's simply J dot B, isn't it?
No.
What is it?
It is this AB integrated in K space.
Surprising.
I will rewrite, just a moment. Let me just finish. And the initial term which we find, gradient alpha kinetic multiplied by V squared. Multiplied by V squared. V squared divided by something, just a minute. Yes. Right.
Minus gradient.
Alpha K multiplied by V squared.
What units here?
It's okay. Why? B squared divided by Nabla,
Mhm.
B equal B. We multiply alpha in units of velocity. About this term, I'm not so sure. Let us check. Actually, we should put something in this, at least in this calibration.
Also no problem units of this.
No, there's no this is no problem of units, of course.
Yeah, yeah.
There's no problem of units. Let us check what happened with this term. It is no problem, of course, too. S, it is 1 divided by time, and we need, maybe it's not so bad, because U,
The last term you need to roll or something. because
B,
I'm-
it's okay. Let me say about rho, I will give you some my comments about rho, just a moment. It is okay too. Why? Because it is U divided by L. U divided by L, this is. So it is B equal B.
Oh, we need to roll
Unit.
somewhere.
A rho somewhere,
To make a velocity unit.
better to write in your equation in form UM divided by rho. Rho normalized. Because your equation of mean field, rho normalized. Somehow.
No, it doesn't matter how you normalize it. But you know, the last term you also need to roll somehow.
No. It is in some sense what I write. It is HI curl J multiplied by this epsilon. What I write. And after that, I can rewrite in this form. And if this delta Mn in reality, I will find what I write. So in some sense, my alpha M, it is just A dot B divided by L naught squared. My alpha M. In order to get in this moment alpha real, I should divide by this. But if I normalize rho by something, in this situation it is my alpha M.
It's a bit.
No, it is.
Sam, excuse me again. So can you write this final equation?
Of
This
course.
simple equation for alpha.
Yes.
Because we have divided by rho. That was not really to divide.
Okay.
by rho.
No. Because we don't discuss rho. For solar situation, we need rho. Okay, let me write simple equation in.
Alpha is equal alpha kinetic plus alpha m
Yes.
divided by rho.
Just a moment. Yes, alpha kinetic. So, equation is for dBdt curl alpha total multiplied by b minus eta algebraic quotient multiplied by curl b. It is induction operation. Alpha total. Again, it's according to our calculation. Equal alpha kinetic multiplied by quotient function algebraic plus alpha magnetic divided by rho multiplied by quenching function algebraic, his own.
But you have also algebraic quenching.
Yes. It is field function, which field and what's his name? Blackman find.
I thought we don't need it because we have the rank quenching form.
No, we check better to use. We can drop it. You're right. If you flux enough, strong, simple, this value small. It is equation for magnetic field, of course. Now equation for helicity. And the equation for helicity has the following form. D alpha m dt equal Q, I should find this coefficient, honestly speaking.
Okay, I know, we know Q.
Yeah, you know.
Yes.
Excuse me. B, Q rho B, equal Q, B, Q rho B, minus alpha total B square divided by eta. By the way, some problem. I think we should take eta A. For colloidal field, if I remember correct. And last term minus divergence flux. Minus divergence flux. And of course, in some layers, important to take into account this term. Tau naught multiplied by RL. At least, of course, we have taken into account in this picture anisotropy of magnetic.
And P
is four terms.
So it's U equal U times alpha m.
I should check just this minus.
Also check dimensions.
Dimensions, okay.
Units check and
No, let's check. Alpha k, units of alpha k, of course. It is just one. Of course, you have got something rho naught. Normalize. We should put in this position rho naught in order to normalize it in good manner. Let us check simple what is right. It should be u multiplied by alpha m. Alpha k, units of alpha k, of course, it is u.
Oh, it's alpha k.
Divided by a, multiplied by b squared. So it is really right.
Yes, you're right.
So, this is how to say what we know until now.
What the physical meaning of the last term?
No, I will explain it very trivial.
It doesn't make sense, I think, to think about all the possible terms at the first instance.
Yes.
If you, I mean, my attitude to these things is to, and that's what we are trying, of course, we do a direct simulation of a physical system that we understand very well, and we do the mean field simulation and make sure the two agree. And we are in the process of doing this in 1 dimensions. We have made reasonable progress on that. If you want to jump to 2D before one is sure, then of course you're a bit on slippery ice. Especially if you're including terms where one is really not so sure about that.
You mean this one?
I mean the last term is the question.
Okay, I think last term important. Because we can imagine situation that shear equals 0. But nevertheless, hard to believe that without large-scale motion, from active region, no, how to say, some flux. Just alpha should produce some flux. We can imagine situation we have on shear, not far from surface for some reason. Because no, if we've got stress-free condition, shear equals 0. Precisely on the surface, right? So it should be, maybe not, if you take into account flux of entropy. But anyway, this two term may be important.
Suppose you know that we have no magnetic helicity and negative kinetic helicity.
No magnetic helicity.
Initially in system.
Yeah, that's fine. And then,
And,
And then,
That's
okay,
the
we know this.
Last time will generate magnetic helicity.
yes.
No, situation is a little bit more complicated. Because
Yeah,
what?
but
We use,
every time I mean, especially,
Right.
no, this is, these are just flux terms. The term that really generates magnetic electricity is of course, this equation. It's this.
right, but actually it's not correct, this equation in case.
It's not the flux, of course.
What?
Which generates in front of the flux.
See, yeah, so it will go, yeah, so this term is probably can be combined, the last term is this term, right? And
You mean this one and this one?
no, this one,
This term?
this term can be combined with this one somehow.
It's
It's
not the
similar.
same.
It's a similar physics.
Because it's gradient.
Similar
It's
dependence.
not the same. It's not the
I
same.
see the gradient, yeah, but
Yes, it's not the same. It's not gradient.
it's proportional to
it
b
is-
squared and
Right, but it's proportional to gradient of kinetic helicity. This is total. It's not the same.
it's only kinetic helicity.
Yes. But I would like to stress another thing. Suppose we have an alpha dynamo, alpha omega, alpha square dynamo. We have got another, no shear dynamo, for example, or omega g effect. In this situation will be nothing, because in general we have got what we have got in reality, 2E dot B. And E may be very different from our expression. So for shear dynamo or for omega cross G dynamo, maybe not the same.
So actually, you agree with this equation, right? Yeah. Except the last term in P.
No, two terms, honestly speaking, actually two terms. This one and this one. But from another hand, from general consideration, this term should be exist. Hard to believe it doesn't exist, actually, huh?
I mean, I just check these things quantitatively, and so in some cases I've checked this. So for example, I actually know already that this time it's not completely right, but I mean,
What term?
and that there is an additional contribution from the antisymmetric part.
Uh-huh.
But that comes under non-Soka conditions. These come under non-Soka conditions. And we have not completed the study yet. These are complicated because there's gauge issues with these fixed fluxes. And so they become important at larger RMs. So we know already that some of these terms break down. I mean,
What term breaks down? You mean at this stage?
Yeah.
Well, this one.
Yeah.
See, will be another, not breakdown. Will be another, isn't it?
Yeah, of course. Yeah, we break
It exists.
Sure. Yeah.
To push.
So it's.
Don't be afraid.
I mean, it's hard to push these things. I mean, it's like I would be saying you should do your heliosseismology, but make it more accurate now.
No, I'm just saying that we have certainly, yeah, we have some model, and I'm just asking for the best model of solar dynamo. I'm not asking for absolutely correct model or something like that, but what's
No, I think it's
best
based on
understanding
this
of
knowledge. Yeah, I
And
think.
that's this, of course, and I have it here, and I have it here.
Axel, I think it's the best knowledge what I wrote. At least today. Maybe for some several.
Well, it's a serious question, when you start doing codes, computer codes, right? You need to put some, real
Some
numbers.
models. Actually, I agree that it's what we've got in reality in large scale today. Today, yes. But of course, many open questions. For example, plausible situation, something follows. Some say gradient rho.
Actually, something email with this paper.
Yes,
Yeah,
just
so-
that comes now for the fifth time printed, unfortunately, the proofs instead of the actual paper, because it's stupid.
Possible, possible additional problems. Gradient rho, alpha kinetic, this question. This term we find somehow. This is road symmetrical regions.
This could be dominant term. What maybe, it's dominant.
Okay, again, Sasha, we didn't check. We understand your idea, maybe you're right. I don't know honestly. Really.
Please advise us how to make a mean field model of solar dynamics.
No, okay, let us write it. I will just check sign. But I know for our calculation with MOS, that the main term nevertheless this one. He's more important. At least he is crucial. He solved all problems. Because he automatically, how to say, yield results.
So this gradient of rho appeared because probably of your definition of alpha m. Why did you need to, can we just put away this one over rho from alpha m? So
you can do it because you've got isotope at this position. You draw, in some sense you avoid, but you know, ее другой дверь, она войдет в окно. How to say in English, I don't know. It is about truth, but I think it's from German. If you try to push truth to door, truth penetrates via window. I don't know, maybe if it's, who is it? It is Goethe, I think, something, I remember, the Russian translation.
Because of all these terms written, saying this T,
Without any...
the last term is dominant.
This,
that's a density scale high.
yeah, I agree. No, not far from surface, maybe it's true. Maybe it's true.
So it's,
Okay, I see.
there's this talk by one of our Norwegian postdocs at 1:15, Niccolo Pocentini. He will be talking
Maybe we
about
should go to it. Last time.
magnetars.